Yeah, okay. So previously we have been working on this prediction. On-policy prediction means that we just want to update the state values. Now we move to control. Control means that we're going to update the quality of action, update the policy, right? So let's look at it. Actually, the process is straightforward. So as usual, we have this reinforcement learning framework. We have this agent environment. We have been learning this state value function. Previously, there's no parameterized weight vector. Now we put this weight vector here. And in the last lecture, we learned this how we can update the state value with this approximation approaches. Now we're gonna learn how we can use the approximation method to update the action value function. So as usual, we can extend our control problem in reinforcement learning to the parametric approximation. Means that we're gonna add this W. Previously we just QSA. Now we add this the vector W, parameterized, right? Then the W belongs to the D-dimensional real number. So this D dimension depends on the if we use the linear function, depends on the order, right? If we use the linear function to represent the above function, so the QSAW, Q hat SAW, is defined as the W transpose W times XSA. And yeah, we can just write down. So different is that we have A now. Previous there's no A, only has state. Now we have with state with an action, the value. So since it's a linear function, we can just do the dot product and calculate them together. The definition of W was the raw. Then we transpose. The definition of W was column. Then we need to transpose it to a row, right? Row times a column. Then we have this sum. Particularly, we will extend the Sarsa algorithm and the semi-gradient TD0 to on-policy control. For these two approach, especially, we're gonna focus on either episodic and continuous. For continuous case, actually, for the continuous, previously in the past lectures, we are always learning the episodic setting, right? So we consider we have an episode, so we have many episodes. We generate episode as a terminal state, and we move to a new episode again and again. Now, what if we have a continuous case? There's no episode. It's a totally online. It's an infinite process. There's no end. How we can update those action value? So for this kind of case, we need to rely on new formulation for the problem with the so-called differential value function. Differential value function is just, get the difference between the current, the action value and the average reward. The average reward is a new term we didn't learn before. Okay, firstly, let's recall what we learned in the last several lecture. So in the VE, the value error, right? In the value, we try to minimize the value error by the SGD. Okay, so what we do is that we formulate this update process. This is a major update equation we used in our algorithm, different algorithm. We use this update, right? So there's alpha is the step size, then this the nabla. FW is the gradient. And also we have this estimated version of SGD. So since this V pi ST is unknown, we use other values to represent it, to replace it. So if we use the UT, we use UT as an estimate of the V pi ST. So if the UT is the Monte Carlo target, then we just become the return of the inside of the Monte Carlo target. Okay, so this is how we design or set up the update process in the prediction approximation. Yeah. So now we do the extension. We extend the state value to the state value and the action, state and action to this UT instead of only state value. Okay. Then the UT can be any approximation of the Q pi ST80. So it can be the Monte Carlo, which is GT, can unstep Sarsa return. So unstep, if you remember the Sarsa named based on the sequence, the trajectory it will use for updating the action. So especially it should have the two SA, reward SA, because we need to use two actions in this two time steps data, right? To update the quality Q value or the action value. Now if we use unstep Sarsa, we can design the update equation in this way. So what we do is that the UT is the unstep Sarsa return instead of the MC return. Okay, then minus this action value function Q hat, the estimated action value function, and times this the gradient of this the Q hat. So with this way we can update the weight to approximate the quality of this action. If the update is one step Sarsa, so here is the unstep. If you use one step Sarsa, the method is called episodic semi-gradient one step Sarsa. So we just expand from the above, the UT will become the RT plus 1 plus gamma Q hat. So this is the next step. So I think this the highlight rectangle should be put on the RT plus 1 and the gamma Q hat, not the later two parts. Okay, so it should be moved to the first two parts of this. So since this represents the one step Sarsa term, so now the UT become the RT plus 1 plus gamma Q hat. The next step Q hat, right? Because we have the current step, we are moving the next step. We have the new action value with the return. Then we can get the difference between the previous step. Then we can update. So this is the episodic semi-gradient one-step Sarsa. With this update equation process, then we can design our first control algorithm for estimating the Q value function. Okay, this is so-called episodic semi-gradient Sarsa. Also remember, we use the semi-gradient. It's not full gradient, right? Because if we are using the Monte Carlo return, it will be the gradient. But Monte Carlo is the unbiased return of the problem, right? But if we use others like TD or Sarsa, actually Sarsa is the special case, it's the extended case of TD. Then it becomes semi-gradient. It's biased. It's not exactly the gradient. Okay, but yeah. So episodic semi-gradient Sarsa. So the process is similar to what we have been seeing. Yeah. So we have this weight. So we initialize the weight arbitrarily. For example, we just give 0 for all the initial weight. Initial state action. So the process is that we loop for each episode, and then we generate initial state and action. Then this can be based on the epsilon greedy. Okay, we choose the greedy action or we choose the non-greedy action. Then loop through each step to generate the update. So since it's Sarsa, you remember Sarsa, so we need to have this pair, the two pair. SA, first you generate SA, then take an action, and observe RS prime. Okay. Then we have this the pair now. So S A R S prime, then A prime, another action. So we have this the sequence S A R S A. If S prime is terminal, there is a one condition. So it's to process to deal with the terminal state, right? If it's terminal state, there will be no next state, right? We can just directly use the return we have instead of adding the R plus this discounted Q value. Okay. Okay. So this rectangle should be shifted to the left to cover R and the gamma Q hat, not this later two part. Okay. And now the normal process is that we choose A prime as a function of the Q hat. So we can follow the epsilon greedy. Either we have some probability to choose the greedy action or non-greedy action. Then we just use this Sarsa update process to update the weights. Then once we update the weight, then we can put the new state to the current state, new action to the current action. So that we loop again. So we will generate a new. We take this action, then we will generate a new state. Then we just iterate, continuously iterate. So this W will be kind of reduced. The weight will be updated, keep updating. Then the overall, the process will be updated, right? Okay. So let's look at the one example, mountain car example. So we have this mountain car. Actually, this is quite famous example or use case in different reinforcement learning. So the setting is that the gravity is stronger than the car's engine or motor. So you have this car. The goal of this for this car is that it needs to move to this target. Okay. Once it moved the target, it succeeded. So the thing is that it cannot, based on its power, either engine or motor, it cannot reach that goal. So it needs to rely on gravity to give some like inertia speed for moving toward the target. So the car needs to use the opposite slope on the left. Use this left side slope to give some inertia to reach this goal. Now the problem is that how we can, what kind of the policy of this car should be. So the reward setting is that -1 for each step. So every time step, whenever it moves one step, then it has a -1. So our goal is that we need to find the minimal return. Okay. And action has three types: 4 throttle forward, 4 throttle reverse, 0 throttle. Means that 4 pedal drives front, 4 pedal reverse drive back, or just stop without any speed. Then there is a dynamics. So it's like it's similar to if we have those kind of greedy MDP, greedy word, the dynamics. We have position x and the velocity x dot. So actually it should be x dot. I use s prime to represent this velocity, position and velocity. This the update is based on these two dynamics. The first one is the position. So xt plus 1, this is velocity, because since this is the velocity means that per time step, the speed of per time step. Since we don't consider the actual unit of the per time, it can be the millisecond, can be per second, or can be per hour. But in most cases, we consider per second. So but we don't care the actual unit. We just consider the time step. Since the speed we are measured by the time step, so we just the current position plus the speed. The next step with this is the step size, similar to the step size, right? What is the position? We will look at another graph later. Then the speed will be updated by this. The current speed plus this is force from the engine, the power from the engine minus the power from the gravity. Okay. So in this way, we can adjust this velocity. Then we use the bound operation. So we give the limit, okay, the maximum, the minimum. The bound, the real bound is xt plus 1 x point x dot plus 1 between this the range. Okay, so this is the basic setting. Now, each episode, the car will randomly start from this the position between minus 0.0 to the minus 0.4 with 0 velocity. Okay, so if you for better visualization, actually what is meant by the position? Position is the coordinate, this x-axis position. Okay, so we bounded the position between minus 0.2 to 0.5, which is minus 0.2 to 0.5. If it reaches to the 0.5, means it reaches the target. And the starting point will be around this minus 0.5. Okay, minus point, the starting point on the bottom of this valley. Okay, so as we setting here, the starting point will between among this minus 0.5. Now we have this setting. What is how we can generate the policy that help this with the minimal time step, minimal this reward to make this car to reach this objective, this goal. So actually, this car need to be hanging around several times to reach this objective. You need to move first and reverse back to here, and move forward and reverse back again and again. So now it will reach the first time. Sorry. The first time it will reach to some point here, and it will reverse back. So every time we will reach it higher and higher and higher, higher and higher. If the car hits this wall, it will immediately have the speed 0. Okay, so it means that this force will not have this xt1. If it hits the hard wall, it will have 0 speed. Then it will just following the gravity to move down. Okay, this is the setting we are having. And so, yeah. Yeah, so this is the setting. And actually, for this kind of a control problem, if we use if you some of you may be familiar with the control theory or some traditional control approaches. Some of you may not be familiar. So even from the standard control theory, it's difficult to derive some very applicable control process for this car. So actually, it has a lot of back and forth. But we can use the reinforcement learning, especially we use this episodic semi-gradient Sarsa to generate the policy. Okay, so let's take like a 15-20 minutes break and continue this example. Okay, since we're gonna have a lot. Okay, let's take a break. We come back at 1:30. Okay. Okay, so let's read our lecture. I know some of you are kind of tired. Actually, I in the business trip, because there's time difference, 8 hours, 9 hours time difference. When I reach there, I experienced jet lag. For several days during the day, I couldn't kind of have enough energy. So in the early morning, like 6 or 3 a.m., I wake up and I put my laptop to work. During the day, my eyes, I feel so constrained. And after coming back, I also have the jet lag again in this week. Like And the Monday and Tuesday, early morning, like 3 a.m., I wake up. I cannot sleep. And during the day, just lost my focus. Yeah, but yeah, since Wednesday, Thursday, I getting better. So yeah, let's continue our lecture. So we have this mountain car example. Okay. This so if you look at this problem, actually our state position, actually the stage consists of the states, like each state is the combination of two features, right? Position and the velocity, and they are continuous. So it can be the continuous and can be the discrete, right? Because it depends on the time step, because we are always consider the time step. It can be the continuous. So yeah. And so for this kind of 2D state spaces, we can convert these two continuous space variable, x and x dot, to a binary feature by a grid tiling. So the tiling, tile coding we learned in the last lecture, right? In this setting, we use 8 tilings, and each tile of a tiling covers 1/8 of the bounded distance. So means that, for example, we have this 2D space. So the x-axis is the, let's say, position. The y-axis is the velocity. Now for this kind of 2D space, we use this is the one tiling. Then each tile is share of this will cover 1/8. Okay, 1/8 of this space distance, either the position or velocity. So eventually, each tile in one tiling will have a kind of different size of the width and the height, right? Because they have the position has different scale, and the velocity has another scale, right? So the unit size will be different. And as a reminder, so we recall that how we define the tile coding. So we have this 2D space. Then we use, this is the one tile. It's similar to, if we just use one tiling, then it's similar to the state aggregation we learned before. Okay, state aggregation. If we use multiple tilings, so now we kind of encode the states in this 2D space into multiple tiles. For example, here, if, for example, we have a particular speed and a particular speed, the velocity in this state, and this state will be represented by 4 tiles or 4 features, let's say, 4 features here. And we're going to use these 4 features to represent this one state in this case. Okay, so, but this is a case of using 4 tilings. But in our setting, we're going to use 8 tilings. Okay, with these 8 tilings, then we can update. As a reminder, we're going to use this, we define the Q value function or action value function as the linear combination of the feature space, okay? Similar to the value function we defined before. Then we can do this dot product, and we'll just do the sum for the two between the weight and the feature. So now how we can generate or define these 8 tilings. Actually, if you look at here, we can simply, for example, as I mentioned already, so we have the x-axis can be the position, y-axis can be velocity. Then we use 8 tilings here. If you count here, 1, 2, 3, 4, 5, 6, 7, And there's another tiling which is located here, 8 actually. And in this example, in this demo showcase, actually there's a small space I couldn't cover, which is located here. But I mean, just as an example, how we can build the tiling. Okay, so for this kind of tiling construction, we call it the symmetric tile coating. Okay, because when we put those different tilings into this 2D space, we kind of use a symmetric way to equally distribute the tires among all the state space, the state space, right? We call it a symmetric tile coating. But actually it brings some kind of bias or deviation to the coding, because we kind of artificially we put some symmetric feature on the coding, the representation, right? So another way is we call it asymmetric tile coding. So we, for example, here we can kind of based on some like displacement, like there's a x, y, x, y axis displacement to place multiple tilings in this way. So if you can, based on some displacement, for example, here, if you look at, we have this rectangle, this square, with this square. So we have 2 tilings. Actually, they are shifted based on the displacement, which is 1, 3. Okay, so this is 1 tire, and this is 3 tires. Okay, so based on some displacement, and you can compare others. They all based on this kind of 1, 3 displacement. With some kind of this displacement, we can generate like a asymmetric tile coating. So this kind of coating reduce the artificial, the diagonal, symmetric, the bias when we do the coding. So back to this problem, how we can design this coding. So we have this velocity range, position range, velocity range. Position range is between the minus 1.2 and 0.5, right? So if you calculate it, the 0.5 minus the plus 1.2 is equals to 1.7. So this is the total distance. And for the velocity, you can also calculate the range, which is so is the symmetric velocity, and the total range is 0.40. So since we are using 8 tilings, and a tile in each tiling will have 1/8 of the total distance. So we can, each unit size, each tile size will be like, so the position is 1.7 divided by 8, which equals this size. The velocity will be equals 0.14 divided by 8, which is 0.0175. So this is the unit size, right? So which means this kind of this size. This is the 1 tire. The size of this 1 tire will be something like this way. But you see here that it's not the square. It become a kind of a rectangle, has a longer width and a shorter height, right? So this is how you can design. And then another issue is that if you look at this tire coding, so for a particular state, for example, we have this state. For example, we have a state here. It will link to the like maximally 8 number, right? 8 tires among 8 tilings, right? So each tiling has 1 tire will contribute to this state representation. So actually, all others, the tires will be 0. Only those activated tires will be 1. So if we, for efficient saving the data. In the practice, in the source code, most of the time, we use hash table to save those data. So we give the enough size of hash table, and we give some, each time we just save the data into the hash table with those the corresponding the coordinates. For example, here 3.6, 7.21. Then we put into a hash table. You use the hash table to save those data instead of using the like 8. Since we have 8 tilings instead of using 8 matrix, so it may have a very big memory use. Okay. And another point is that when we design this tile coding, so yeah, also yeah, the displacement, how we can decide. Most of the time we use the asymmetric tile coding, okay, to reduce those some artificial bias. And for this designing this asymmetric tile coding, actually there's a displacement size. How we can use those displacement size? Actually, there's some research, a lot of research in the past 20 or 30 years, a lot of research on this part. What kind of number displacement are better for constructing tile coding? So if you check those related research results, most of the time we use the odd number, like 1, 3, 7, 9, those as a displacement number. So it should be the largest number should be the larger than the 2 to the power k to the power k. Yeah, the k is the dimension. So since actually in the implementation of the tile coding, there's a lot of points we need to take care of. So there's already some open source code there. Even from the author of the textbook, they already open source these tile codings, either C code or Python code, or is already there. We can directly use. What they open source is that you can just either copy their source code or include the Python file. They define this function and the hash table, the class. So we can directly use their function, the tires, then IHT here to represent whether we want to use the hash table or just the integer number to index the data. Then we give the number of tilings, the number of tilings you need to use, and floats. Floats means that in this 2D space, the coordinate in this the actual state, which location you want to encode it into the tile coding. And there's ints. Actually, most of the time, this is optional, but in this our reinforcement learning, we usually put the actions into these ints. This should be the list, okay? So both floats and the ints. So actually, they use the floats to represent the type of the data. Ints to represent this integer, because the action, right? Action usually we use the index to represent the actions. But I guess when they design the open source code, because the Python itself originally have this issue of the type, right? Because when you design a function, you don't know the input, the parameters type. Sometimes it's a kind of very frustrated, right? When you use it, you don't know the type of the parameter. So they directly use the name of the type, floats and the int. So actually, when we call this function, the tires, we give the class an object of the hash table. So actually, this object is the hash table, which represents a memory space. We're gonna build a hash table there already. Then we give the number of tiling, then the coordinates. For example, in our case, it should be position and velocity. But here, 3.6, 7.21 is just a random number I just put here. Then we shall put another one. In our case, there's an action. The action should be based on the 3 actions, right? The either force rotor forward, force rotor reverse, or zero the rotor. Okay. So we put them. So actually, in the hash table, we just both floats and ints. These two the pair of this data will be saved in the hash table. Then once you put here, it will just return you the index number of this hash table. Okay. So when you put more and more data, like the first state, the second state, third state, multiple state into this hash table, it will just keep kind of using the memory space of this hash table instead of using the matrix that we are showing here, the higher matrix. So if you change to another number, then some of this tiling, the index number will be changed. Okay. So you can check this link for this open source code. Let's just take a look at it. So they have this tile coding software. They have the Python version and the Lisp version. They also have this C and C++ version. And they also use other library based on some software from another university. So what they do is that as I mentioned, we can first build a hash table with some memory size. So this hash table has this 1024 stack size. We put it here. Then we just directly call this hash table, the tires, give this build object, give the number, and it will return the indexes. Okay, this is several example how it would work. For example, if you put this number, this is the 2D space number, it will generate the first 8 position for saving this number in the 8 tilings. Then if you just alter a little bit of this number, 3.7, then because we are using the 8 tilings, actually some other data are not changed. Only a particular tiling, tires in the tiling will be changed. In this case, actually, in the center of the 3 tiling, the tire will be changed, will become 8. Okay, slightly alter the data, then we will have a new index number. Similarly, if we have this larger number and more deviate from the previous saving, we have a higher this index number. Okay. Then if you continuously save the data, the index number will keep increasing. Okay. Yeah, this is how we efficiently utilize the memory by the hash table. So actually, there's if you click here, you will see the source code level implementation. You can directly copy the code from here. This is the code to generate the hash table plus IHT, and this is the source code of the tires. How it's generated the tires index number, but so internally you can actually from their implementation, it's a little bit different from what we learned from the theory, from the tire coding theory. Okay, in their implementation, they kind of rescared the number of the coordinates, and yeah, then put into hash table. Okay, this is how we can use this tire coding for mountain car. So now while we have all these settings, now we are ready to use this process. So we can generate an episode. We can have an episode, then we we kind of step by step to update the weight vector that will also update with the policy, right? The Q value. Now, if you look at the data, so the first one, let's particularly look at the first one. When we reach the step 428, we have the 3D, right? The position and velocity. Our target, our goal is to reach is a green. Yeah, it's green, right? Green target, right? Our goal is to reach the green target, which is the peak of the mountain. And our starting point is somewhere here, actually, because it's minus 0.5, which is located somewhat here. So if you look at the first step for the height of this diagram is that the Q value, okay? The Q value, which actually is approximate to the time step, because each time step will have a -1, right? Because the Q value, if we have a -1, actually the Q value itself will be the minus number. Then we put another minus and become positive number. That's why we have this 4, the positive number here. Okay. Now, if you look at the initial step, you will see the starting point actually is in the center of this like a volcano shape. So the center, initially when this car is kind of moving around, it just check the surrounding information. You just move the top and the back, move top and back, move to reach some height and come back, move some height, come back. So we have this kind of like the value, step side. Okay. Now, if we continuously run the simulation, like for episode with the 12, the shape become more and more close to our optimal state, the optimal. So if we run the simulation to 9,000 episodes, it's large enough episode to reach the good policy. As you can see here, the peak of the 3D, which has the peak number is 120, means that this point is the origin point, starting point. So because since we are running this episode, so the starting point will have accumulated the minus reward, right? Because every time the hanging around, so the car will move to this valley, the bottom point. The maximum number is 120. So the goal here is that if you look at this, if you start from different position with the different velocity, you will have a different time step to reach this position, the height, right? This position. So for example, if we have a large enough velocity, so this velocity including both the engine power and the gravity power, right? If you have enough the velocity from here, we can see that. So the car can directly from some position reach to the goal. Means that the origin point is from here. Means that if the car is on some here. If you look at means that the position, if you cross check the, for example, position is here, then we have large enough velocity, means that this car is somewhere here, and we have a large enough velocity, then we can directly reach the goal. So in other cases, if we have farther from we close to here, then we cannot directly reach the goal. Actually, we need to hang around, have the more time step to reach the goal. It means that we need to back and forth multiple times to reach the goal. So this is so eventually actually the algorithm generate optimal kind of estimated optimal policy for how this car in each position, in each state, with different velocities, what kind of the optimal policy of this car should use. Okay, this is how we can use the episodic semi-gradient Sarsa to get the optimal policy for this mountain car example. And another like this data learning curves in mountain cars. So here in this figure, in this this process, we just check what is the time step, the reward, the quality of this Q value, right? The Q value. So we also want to check what is the time step, the impact of the time step. We vary this alpha from 0.1 over 8 and 0.2 over 8 and 0.5 over 8. So different from previous setting. Now, since we are using tire coating, the time step need to be divided by the number of tires, okay? The number of timing. Here in this figure, if you look at here, so this actually this alpha equals 0.1, 0.2, 0.5. This 0.1, 0.2, 0.5 are the epsilon, okay? Because since in the algorithm, actually we put the epsilon greedy policy there. So we can either choose greedy policy or non-greedy. So this is the decimal number represent the epsilon and divided by the number of tilings. So this kind of shape to decide the time step, which is different from the other settings that we learned so far. Then as you can see here, clearly we see this when alpha equals 0.5 divided by 8 as the best like performance, which is like in the previous data when we look at it about 120, right? So when we look at here, this is the step per episode, also close to the 120, which is somewhere here, right? Means that we reach the optimal step. So with that time step, this is the smallest time step we can reach our target from the origin point, right? Okay, so this is the example of the mountain car with the tire coating, or we can use tire coating in this mountain car. So if you look at here, the tire coating, similar to the previous one, the polynomial basis and the Fourier basis, right? So the tire coating will affect this Q hat and the gradient Q hat. Okay, the Q hat, both Q hat. The tire coating, then actually the number, this Q will become the linear combination with W with the tire coatings, the features. So we see that we have 8 tire coating, so you will have 8 elements vector, and this W will also have 8 elements. Yeah, 8. Yeah, it's not 8 plus 1. Okay, this is how you can use the tire coating to get the optimal policy based on this algorithm. Next, we're gonna move to this extend the previous so actually previous was a one-step Sarsa. We just extend the previous one-step Sarsa to n-step Sarsa, semi-graded n-step Sarsa. Similarly, we can use this n-step return. Previously, we just used one-step return. So we calculate the next step to the previous step, the difference, right? Then now we use this n-step Actually, if you remember how we define this n step, we use this gt to t plus n to represent the return of this n step difference, where gt to t plus n equals this one discounted reward, right? And the last item will be discounted the q value. And also we need to consider the terminal state. If we reach to the terminal state, there's not enough the reward for calculation. We just use the return. And also there will be no quality value, q value of the terminal state. We just directly use the return instead of this gt to t plus n. So this is the setting. If you remember what we learned before, actually we carefully check this gt to t plus n, how it can be calculated, right? Step by step. And it also has some features of we need to wait until some data available, then we can update. Actually depends on the number of n, right? If it's 2 steps, we need to wait 2 steps later, we can update previous the value. If it's 3 steps, we need to wait 3 steps later to update 3 steps before the date. Then this is the algorithm for this episodic semi-gradient n-step Sarsa. And if you remember n-step Sarsa, it will not be like strange for you. Since, as I mentioned, we need to, when we design the Sarsa, n-step Sarsa, we need to consider 2 points. One is the terminal state, and another one is the gt to t plus n, the n-step return. Okay, we need to wait until some return are available, then we can update. So then, apart from those the similar parts, then one difference is that now we actually have this another parameter to consider, positive integer n. Previously we have this positive integer n. Previously we didn't have, right? So yeah, because this is n-step Sarsa, so we need to consider this which step you want to go, right? Then others are the similar. We just initialize this weight vector arbitrarily. Most of the time we just use 0. Then the process is that, as I mentioned, we need to consider the 2 points. One, whether it's the in the terminal state. If it's not in the terminal state, we can do the n-step update, right? If it's in the terminal state, then we just put the t plus 1. So we just in the terminal state. We don't need to calculate those n-step return. So the update process is here. We calculate this n-step accumulated n-step return, the g, and the g plus the current q value, update the g if we have enough, if we are not in the terminal state. Then we just rely on this update. Similarly, this q hat can be different coding, okay? Can be, if it's a linear function, it will be some like a polynomial, Fourier, or tile coding basis. If it's a non-linear function, then it can be updated by the neural networks. So with the multiple layer neural networks, right? So it will become deep reinforcement learning scope. So with this algorithm, then we can have this the performance we can check for this mountain car. So we apply this algorithm to this mountain car. So firstly, we just check the n equals 1 and n equals 8. If n equals 1, it just equals to the previous steps. So the first algorithm we look at. Then if n equals 8, will be means that we n step to look forward, to look back, right? So after n, the 8 step, then we update the previous Q function or action value function. Then obviously, if we look at here, the larger n is better better than the small n, means that the larger n will converge faster than the smaller. So eventually, actually, they will converge to the similar level, but the larger number, the larger the n step, will have a faster learning speed, learning rate. And also, we would like to check the different combination of the step type and the step type and the step of the Sarsa, right? So if you put different n here with the different step type, we clearly see that. So this is alpha times the number of tiling, since as I mentioned previously, the step size is decided by the epsilon and the number of tilings. So here we use this alpha times the number of tilings to calculate this step size. So you will see that if you in different step size, so different number of n shows different. In particular number of this step size, a particular n has a better performance. For example, if this step size is smaller than somewhat 0.6, then n equals a is better. If the step size is between 0.6 to 1.1, maybe 1.1, then n equals 4 is better. Then so overall, the n equals 4 is better if they adjust the step size. So it has the fastest learning rate, okay? Learning speed. So this is how we can use the semi-gradient n-step Sarsa to further improve the learning speed or learning the better performance. Yeah. So about any questions? Yeah. Actually, if you remember what we learned before, this algorithm should not be too new for you. Most of the process we already learned. The only difference is here, the update. You parameterize the update, right? Yeah. Okay. Now we move to the new problem setting for continuing tasks. So in the past, actually from the beginning of this semester, most of the time we focus on the episodic and discounted reward. We didn't consider continuing tasks without discount. So now we are moving to this new problem setting for this continuing task. So means that a continuing task without discount means that the agent cares both current and the future reward. So there will be no discrimination between the current reward and the future reward. We just care the long-term, everything for some task. So we will look at some example later. First, let's look at the setting. So since we are considering this a continuing task without discount, so it's a clear difference, right? Previously, it was episodic, discounted reward. Now, episodic means that we will have many episodes. Then each episode has the end, the terminal state, right? Terminal state. Then we will restart that. We will start a new episode again. Now we just have one continuing task without discount. So the rewards will not be discounted. Every reward is counted. Okay. So we define this new setting. We call it average reward. Instead of using the discounted reward, we're gonna use average reward as a kind of estimate for the performance. So in particularly or specifically, we use the quality of the policy pi is defined as the average reward denoted by R pi. So now previously when we design the quality or the action function, we used the return, right? Discounted return. Now, the quality of a policy pi, which is the action value function, becomes the average reward. We used R pi to represent. Then mathematically, we define it as this way. So what we do here is that we start from the initial state as 0. Then we generate a series of actions based on the policy pi. With this condition, all those rewards will be calculated. Then we sum all the rewards together and get the average. So if the h reach to the infinite, so this is the definition of this average reward. So the one particular point is that this definition point out that this average reward should always start from the start state. Okay, it will be start from start state and continues to infinite like time step, and we calculate the average reward. So we can rewrite this one to a little bit because the expectation itself already has the average attributes. Okay, the expectation, right? If you consider those each step we have a reward, each step we have a reward, then if you from a long-term point of view, you can get the expectation of this reward actually is the average of the reward of multiple steps. So we can just simplify. We just use let the time step reach to the infinite. Then we can directly get this expectation. Then with this term, we can further extend to some kind of MDP or Feynman equation style of calculation is average reward. So we have this dynamics. We have all the possible actions. Then the new term is this mu pi s, is all the possible states. So as you can see here, this mu pi s represents this definition will cover all the states. Since we are considering the horizon there's no ending of the horizon, but we will keep going. So it means that all the state value will be considered. Then the definition of this mu pi s is in this way. So we will consider infinite horizon. The probability of this so means that ST will be every state, possible states, as much as possible in this continuing task. So we call it MDP is ergodic. Okay, a new term, ergodic. If you learn the random process, probability and random process, or some other probability subject, of course, you probably will see this ergodic. Okay, in the random process, when you design the random process, is the one feature of a random process is ergodic or ergodicity. Means that we're gonna visit every possible state. It will cover all the states because since our horizon is infinite. This is the definition of this pi theoretically or mathematically. And for this average reward in practice, we're gonna use so-called differential return. We use here, okay, differential return. For this average reward setting, returns are defined as the differences between reward and the average reward. So when the time, for example, because it's a continuous task, for a particular continuing task, we will have keep updating this average reward, right? Once we have each step, and each step we also get one particular reward. Now we consider the return. The return will be the differences between reward and the average reward. Okay, this is the definition different. So now that for this case, the GT return becomes the difference is between the current reward minus the average reward for this continuing path. Current reward minus average reward. Current reward minus average reward, or AR, okay, infinitely. So it goes continuously. So this is the GT. The definition becomes this case. We call it differential return. Then with this GT is a return, right? So as you remember, our reinforcement learning framework, our objective is always to maximize the return. Then with this return, we can recall or redesign our value function as differential value function. So then since we have this differential value function, then we also have a series of this Spearman equation. There's a without gamma, since our setting is that there will be no discount factor, which is gamma, right? So here you can see that this is a set of Spearman equations without gamma. If you look at the first two equations are the Spearman equations, general Spearman equations. The later two equations are Spearman optimality equations. So they put this greedy operation, action selection, okay? A, maximum A, so it becomes the optimality. So the only difference is that, so maybe I need to remind you what is the Spearman equation, the original Spearman equation, and the current setting is a little bit different. So originally, previously, these are, actually we updated this part. Previously, this just reward, just R itself, reward itself. Now we consider this return as the reward minus average return. Okay. Previously was just R. Later. Yeah. Previously was just R. Now it becomes R minus average reward. Reward minus. So also the gamma disappeared. Previously, the gamma is in front of this V pi s prime. So they kind of discounted the current. I mean, the neighboring the state value. There's no discount anymore. Similarly, the action value or Q value, we update this R minus R pi. Previously, in the previous setting, MDP or episodic discounted setting, we only have R plus discounted the Q value, action value, discounted gamma. Now gamma is disappeared. The others are just similar. So here we just consider maximum pi, means the greedy action from the pi. Okay, this is a new setting, new the Spearman equation based on new setting. Similarly, for the TD errors on the differential return, we also have a new update. The new two TD0 errors become, so for the state value function, it becomes in this shape. For the action value function, in this shape. So you see here, the difference is that we are using the average return, AR here. We use the R bar to represent, R bar represent, okay? So this is the current return minus the R bar, the average return, plus the estimated, the current estimated the state value minus the previous time step state value. So this is the one major difference. We are using the differential value of the return. Similarly, for this action value function, we also have this setting. We added this minus R T bar. So with all these new settings, now we can update previous designed algorithms with differential versions. For example, if we use the differential return in Sarsa, we have the differential semi-gradient Sarsa algorithm. So this is what we are designing here, differential semi-gradient Sarsa. So don't forget that our target problem set is as a continuing undiscounted setting, right? Continuing undiscounted task. So if you can imagine what kind of tasks are these, it can be like online service, like the web service, or like advertisement service. You will just continuously recommend the product, or you will receive some feedback from the customers continuously. There will be no ending. Yeah, different kind of applications can use this kind of settings. Differential semi-grid. So let's look at this algorithm in detail. Okay. So now we are having a new step size beta for AR for this R bar. Okay, this average reward, average return. Okay. So this beta, we have a new step size beta. Now, also one distinct feature is that there's no episode anymore. We will loop for each step. There's no, previously we have two loops, right? We loop the episode, then we loop each step. Now there's no episode anymore. We just loop for each step. Step 1, step 2, step infinite, large enough, then we can get some data. So since it is Sarsa, whenever you see the Sarsa, means that we need to have two pairs of state action. Okay, as we have the state, we give the action, we have a reward. Then we move to a new state, a new action. Then with this new state action, we can update previous state action. So similarly, we take to initialize the state S and action A, we take an action, observe R as prime. So we have the current state action. Then we take this action, we receive the R, then we move to the new state S prime, then we choose a new action A prime from this policy. So this choosing action, a new action, can be based on the epsilon greedy. Okay. So with this setting, now we can update. So previously, when we update this return, there's no this R bar item or part here. Now we are using this R minus R bar, the differential reward. Then plus is the new state action value minus the previous action value, then update to this C term. This is delta, right? Yeah, delta. Then we use then we update. Actually, this average reward need to be updated, right? Average reward need to be updated. And previous calculated average reward plus the time step of this new calculated reward. And we updated this average reward. Then with this delta, since this delta serves the differential part, then we can put to here. Then this is the major update equation we looked at previously, right? Is Sarsa update process. Then similarly, if you this Q hat, if you use different, like it can be either linear function or non-linear function. Linear function, it can use multiple different kind of feature construction approaches, right? The polynomial, Fourier, or tile coding. Yeah. Then with that way, you can update this. If it's non-linear, it becomes a deep reinforcement learning. You need to use the design the neural networks to update those states. After that, we just update the current state. Okay, this is the differential semi-gradient Sarsa. So let's look at an example. The example here we are looking at is the access control queuing task. So look at this example. We have assumed that we have a server, 10 servers, machines, for example, like a cloud computing server. And we also have this is the queue, the job queue. So the tasks or jobs will keep coming to this queue. Then each task, each job has a priority. So the higher priority means it will have a higher reward. Lower priority will have a lower reward. For example, P8 in this case will have a reward 8. P1 means a reward 1, lower priority. A little bit. So sometimes when we look at this setting, I don't know whether I need to put the higher priority as define the higher priority with P1 or P8. But since we consider reward, so I just put P8 as a higher priority. Okay, the larger number means the higher priority, P8. So now we have these keep coming jobs. So you can consider those, each job is from a customer, a subscriber. So this customer is using pay the subscriber service from like a service provider for this server, computing server. For example, we can rent the GPU server from Google or Naver or any other like those computation resource provider. Now, when you submit the job, they need to decide. They may have multiple levels, the customers. For example, if you are like company customers, perhaps you pay more to get the more computing resources. If you are an individual subscriber, then you pay less, like less computing resources. If you are a free user, then you have maybe you don't need to pay. You have a lowest priority. So now the agent here can either accept or reject a job from this queue. Then this is all known information. So the server side, we have either two states, busy or idle. If it's busy, it's the red color, idle become green color. So the other like dynamics we don't know. Like for example, the arrival rate, we don't know how much, how often, how frequent the jobs will arrive to this queue. So our goal is to maximize long-term reward. Also, another setting is that each time step, one busy server will become free with probability equals 0.06 on each time step. So for example, 7, this number 7 server will have like 6% of probability be free for each step. So it means that it finished the job, calculating job, then it's ready to serve. Then our goal is to maximize long-term reward. What is the because for those kind of cloud computing services, those like a data center or those servers are always running, then they are always receiving the customers' submission, right? So actually there's no terminal state. So you need to keep receiving the new jobs, right? Now our goal is to maximize the long-term reward. For this kind of problem or task, we can rely on the new setting we just designed, the algorithm. So if you look at back, we need to design this initial weight and average reward. Initially, we just keep the 0. So our goal is to maximize our reward, right? Now, from long-term point of view, this is the way. Then we can just use this process. The state is represented by the server. Okay, is busy become 1, idle become 0, and it depends on our definition, the state. And the action is from the agent, whether we accept or reject. Once accept, then the state will be changed, right? So the state, we can consider the state is the 10-dimension, the binary state. So each either 1 or 0, idle or busy. Then once we choose an action, whether reject a job or receive a job, then one of the number will flip either from 0 to 1 or 1 to 0. From 0 to 1, not flip here, just from 0 to 1 if we receive. If we reject, the current state will not be changed, right? Now, then we just choose an action based on the current policy. Then we can just update this, the delta, then update this weight. So we keep running. So eventually we will have some converge the data. For example, here, this is the policy generated by this differential semi-gradient Sarsa. I use the DST Sarsa. So you see here the policy. If you look at this policy it's generated, it's kind of from long-term point of view, it gives the maximum reward for this company. So if you look at here, when we have a 50% the free server, idle server, we can accept any jobs, right? If we have the we have like below than 50% server, above the 30% server available, we need to reject the priority 1, the job. Then when the server, the number of server is below than 30% and above the 10%, we reject the priority 2. Then eventually when the server is below 10%, we only accept the highest priority jobs. So this is the policy generated. So it gives the long-term reward, the maximum long-term reward. Okay, other settings are here, alpha, beta, and epsilon. So it's a kind of how we use the previous algorithm. Then after 2 million steps, it's large enough, right? And the learned average reward was about 2.31. Actually, it's not that over expectation. Actually, it's not quite low, right? If you consider 1, 2, 4, 8. So the long-term reward with the average reward, the profit will be 2.31. Then if we look at this differential value of the best action, this shows the value function, the value of the function, how the value function changes when different priorities of the jobs are accepted. Yeah, so this is one of the paths we can use this new setting to design the policy. So, so this is a very simple case. You may extend this kind of case to like more advanced version. For example, you may have multiple queues, or also here the server, each BD server become free with probability. So this kind of a setting is kind of simplified. So you need to consider the job size, right? And the computing resources. So maybe each server may have a different computing capacity or capability. So also need to consider the size of the job. So which it need to be allocated. So then actually in the algorithm course, you already learned the job assignment algorithm, how you can do. It may combine the reinforcement learning with those traditional algorithms together. So then you may generate multiple policies for different like kind of jobs, different kind of size of job, different kind of server. Yeah. So yeah. Now we move to the next topic, which is the differential semi-gradient unstep Sarsa. So it's kind of extended version of the one-step Sarsa, right? Previously we just see the one-step Sarsa. It's now unstep Sarsa. Similarly, we have this. This is the unstep return, and we also, as usual, we need to consider terminal state. Then the unstep GD error becomes the GT minus. So especially this return, the unstable return become different compared to previous one. Previous one is just discounted the return. Now it becomes the differential value. The current return reward minus the average reward. Current reward minus the average reward, and plus the Q value. Okay, this is the major difference for this setting. Now we can design this algorithm, which is a differential semi-gradient n-step Sarsa algorithm. Actually, this process is simplified compared to the previous one because they just simplified the terminal state checking, but the overall meaning is the same. So, yeah. So the difference is here. We need to consider the n-step differential reward. Okay, this is differential reward. We need to accumulate n-step away differential reward. Then with this reward, we update the average reward. Then we use this update, parameterized update process. Yeah. So yeah, that's for the new knowledge today. Any questions? Okay. So yeah, we summarize what we learned today. We extended the control problems in reinforcement to parametric approximation of action value, as it's shown here. Previously, there's no parameter of the weighted vector. Now we have this. If we use the linear function, it will become in this way. So with this setting, we extended the Sarsa algorithm and the semi-gradient TD0 to on-policy control. So we designed the two algorithms, right? The one-step Sarsa and multiple-step n-step Sarsa. For continuous, so now after that, we also extended our knowledge, the scope, the problem set into the continuing undiscounted task. So for that case, for this task, this kind of task, we rely on a new formulation for the problem with differential value then by using the average reward. With this new setting, we designed the two new algorithms, which are differential semi-gradient Sarsa and the n-step Sarsa, respectively. Okay, yeah, that's all for today. And yeah. So for your term project, I checked your term project. Many of you have either you are doing by yourself or you organize a team, and each team has different topic. So I don't know how much you have done, but one thing is that depends on your quality of your work at the end of the semester. So apart from this, the evaluation of this course, so your term project will be evaluated based on multiple metrics. I will specify in the iCampus. I will announce it. We will based on the importance of the topic and the solution you find, whether it's like differentiate yourself from others, or completeness, whether to what degree you complete your proposed work, and the final presentation, the presentation how you present your work, and also include another part is your report. So for all those for the presentation slides, the template and reports template, I will upload to the iCampus. You can follow for your final report. So some of you choose the kind of traditional task. Some of you choose some very challenging task. So yeah, depends on your progress. So you can try your best to finish your term project. And also one point is that at the end of the last day of this course, so every one of you every team will come to the front, present your work based on your presentation and the multiple metrics of your work, and I will give you the points, the score for your term project. And also on top of that, depends on the quality of your work. I may choose, depends on how many of you, I may choose 1 or 2 or 3 work, like extend them to help you to be published in a conference if you prefer. Okay, if you want to. Depends on your intention. If you don't want to, that's also fine. If you want to publish in conference, if it depends on your quality, also I need to evaluate your quality of your work. If it's publishable, I will try to help you to publish conference. So if the paper got accepted by a conference, I may be able to support your cover to present your work in the conference. Okay, that's what I want to share. Okay, thank you for your attention, and see you next week. Oh, by the way, next week we'll have a quiz for the knowledge we learned in the recorded lecture, and today we have a quiz. The quiz will have 5 questions, single select multiple option question. Okay. Okay. Thank you.